Hi everyone, and welcome to our talk on visual representations and the potential effect on the cliff effect and dichotomous thinking. My name is Lonnie Besançon, and I'm happy to be presenting today on behalf of Uni Healthcare, Satu Healthcare, Matthew Cooper, and Anders Innemann. Let's start by introducing the notions in the title of our paper, and in particular the notion of the cliff effect. In our field, we validate new interaction techniques or new visualization with user studies that help us collect data on accuracy, completion time, learnability, subjective preferences, workload, fatigue, etc., etc. The data can either be qualitative or quantitative, but we usually try to make inferences from our data to show that what we have developed actually works. And this is not just specific to our field. Most scientific fields rely on a study of a sample of the population to try to infer knowledge for the whole population. To generalize from the sample to the general population, inferential statistics are very often used. A specific tool of inferential statistics is p-values, which help to determine if the results are statistically significant. Another one is confidence intervals. They help to provide information about statistical significance and effect size. There are many other measures that could be used, but we'll focus mostly on these two, as they are very commonly used by scientists. The way we should interpret them is the following. When the p-value is very small or the confidence interval is very far from the baseline, we should have a very high degree of confidence about our results, and this level of confidence in the results should decrease as the value change. But this is how we usually interpret them, with a full confidence up until a point, and no confidence after this point, and for all the other values. This is what we call the cliff effect. It has been documented for a while, already in 1964 by Rosenthal and Geither, and has been heavily criticized in the scientific literature as well. As a proof of the importance of the topic, this Nature comment was actually the most ever shared scientific article on social media, pre-COVID. The cliff effect leads to dichotomous inferences, and they have several very negative effects on science and on scientific publication. The first one is called the file drawer effect, which means that papers that present inconclusive evidence are often much harder to publish. Another very negative effect of dichotomous inferences is that they can lead to a replication crisis, a term that was coined in 2010 when it was found that many scientific studies were difficult or even impossible to replicate or reproduce. Why do dichotomous inferences actually accentuate the difficulty to replicate? Well, let's consider that multiple researchers in different institutions, they test independently whether a certain drug can help against a specific disease. And they all use dichotomous inferences. In our imaginary case, they would have study number 2 and 3 failing to replicate the results of study 1. And because the findings do not converge, it's very hard to conclude anything, especially if they did not report their results properly. But if instead of such a dichotomization, researchers quantify the degree of certainty exactly, study 2 and 3 do not fail to replicate anymore, and a meta-analysis of all study would allow us to conclude, perhaps conclude, or tell us that more studies are actually needed to conclude. Now, an interesting thing, when I mentioned all the issues about dichotomous inferences, on which I focus now for a while, is that people often tell me that there's no risk of a replication crisis in their field, or in our field then, or in computer science in general. Even after I presented that paper at OldCai 2019 showing that HCI mostly relies on dichotomous inferences in how we interpret results, people still told me that there was a very, very low risk for HCI to suffer from a replication crisis. So we went beyond this with Andy Coburn, Piotr Gisevich, and Carl Goodwin, and actually showed evidence of all the threats of a replication crisis in empirical computer science as a whole. So visualization and HCI are not immune to these issues. However, the good news is that visualization can actually help in this regard, and that's the focus of this paper. As we saw, a major problem is the cliff effect, this sudden drop of confidence once we pass a specific threshold in inferential statistics. And visual representation can help alleviate the cliff effect. The cliff effect has been quite extensively studied, notably to find if confidence interval could help, for instance, but most studies are old, and ironically enough, they're very hard to replicate because of unclear or not well-reported instructions given to participants, or because of the manual classification of the results, which are very, very hard to reproduce. Most of them are also very old, so old that they were even conducted on pen paper, imagine. In contrast, here we propose a complete reporting of our experimental design, 2 pre-registered studies, and a Bayesian analysis of our results to avoid having to do a manual classification of results. So let's start with the first experiment and its 4 conditions. The first condition is a textual version of the p-value and the confidence interval. The second condition is a classical 95% confidence interval with the bars at 95%. The third condition shows a gradient confidence interval, with this first part actually showing 95% value, and we then show a gradient of all the other CIs, which is the part that I have highlighted now. By doing so, we believe that we can possibly increase the understanding that confidence intervals can go further than 95% and that other values are actually possible. And by using a gradient, we make the 95% limits harder to see and therefore possibly decrease the possibility to interpret these dichotomously. One of the issues with the gradient CI is that the width that we use could be misleading in the sense that participants could interpret them as having the same probability to find the true value or the mean anywhere. In comparison with the violin plot, we've visualized the uncertainty regarding the estimation of the mean, and this is representing with the width variation that we see on this plot. And we also plot other confidence interval at the end with a gradient. Our experiment was run online with the following set of instructions. A random sample of 50 adults from Sweden were prescribed a new medication for 1 week. Based on the information on the screen, how confident are you that the medication has a positive effect on body weight? And here we consider increase in body weight. And participants then had to put the level of confidence here on the slider. We, of course, didn't show any initial value to avoid potential biases. We had different sets of p-values that you can see from this graph to this graph, for instance. So in total, we had 4 conditions and 8 different sets of p-values. We sent this around on multiple platforms and got a total of 114 participants. We had to remove 1 participant because they entered nonsensical demographics. We also invited participants from different disciplines and tried to group them in different categories. For instance, machine learning and stats researcher, Viz and HCI researchers, and other for natural sciences or social sciences researchers. And here are our results. So we mapped the different p-values that the participants saw on the x-axis and the confidence level on the y-axis. And if there was no clear effect at all, we would expect to see a straight line showing a linear correlation between the p-value and the confidence in the results. But we clearly see here that it's not the case. However, looking at both the zoomed-in version and the figure as a whole, it would seem that both the gradient CI and the violin CI are less cliffy. They are closer to a straight line than the other 2 conditions. Surprisingly, and contrary to other past findings, classical confidence intervals are very cliffy, even more so than textual p-values, which we didn't expect at all. We also asked participants to rank their preferences, and it seems that classical CIs and violin confidence intervals are the favorite options, probably because participants are used to seeing them. There are other cases when dichotomous interpretations can happen. Let's look at this one. Researchers are usually confident of a difference between A and B when they see that. Here the confidence might start dropping, and now we see another cliff effect. For all of the values that you saw, people will probably report that there's no difference between A and B. So we ran a second experiment, this time with 39 respondents. We again grouped them in different categories, machine learning and stats, Viz and HCI and other. We also removed the textual p-value condition, in this case for a more discrete version of the violin plot. And here are our results again. If there was no cliff effect, again, we would expect the results to look like something like this, a straight line. But we see again that it's not the case, although we see some interesting behavior. First of all, the cliff effect seems to be smaller, although that might be an artifact of our smaller sample size. Yet this could give us some evidence that if we make boundaries fuzzy, comparison would be more difficult, in particular when comparing 2 CIs, and so people would tend to be less dichotomous. The increase of confidence for continuous violin plots we see as the p-value decreases is likely to be an artifact due to our small sample. Still, it should probably not be read as an increase of confidence, but rather as constant confidence. The drop in confidence is again the largest with the classical CI, but also with discrete violin CIs. So gradient CIs and continuous violin CIs seem to be less cliffy overall. In terms of preferences, the discrete violin CI seems to be the one favored by participants. So after talking so much about dichotomous inferences being problematic, I'll try to avoid concluding by saying that p-values and classical CRs are cliffy and that the other investigating representations are not. Let's try to be a bit more nuanced and introduce some shades in these results. It seems that at least gradient CI and violin CI could help reduce the cliff effect, and therefore perhaps help scientists interpret and communicate about their own results. The case for discrete violence CIs would need further investigation, and overall we would welcome any attempt at replicating our investigation. Nonetheless, there are other factors to consider in what is presented in scientific papers. For instance, violence CI would take much more space than classical CIs, and if page limit is a concern, they might not be ideal if many different results are presented. Although nowadays things are pretty much clear, and I think I've seen papers, I've read a lot of papers that present violence CIs like this, and I don't think it's really an issue. But beyond how we understand our data, which was the focus of this paper, one thing that is particularly interesting, I would argue, is how we communicate it. So we might understand our results in a non-dichotomous fashion, but still communicate it in a very binary way. And this was already the focus of this old Kai paper I presented. But I believe that there's more to it than just looking for the word significant in there. In particular, the specific words we use to describe results can increase fuzziness and uncertainty, or the opposite, increase how sharp or certain a statement is. And this is also something that I think is fascinating future work, and that I started investigating with Yvonne Jensen, Andy Coburn, and Piotr Desevich. The preprint is available online if you want to take a look at it. Once again, we have much more detailed results in the manuscript and a full GitHub repository of additional analysis, so I would like to invite you to take a look at them. I'll now be happy to answer your questions.